All right, hello everyone. Welcome to Chemistry Chapter 11, Lecture number 1. In this lecture, you're going to need your lecture note printout for Chapter 11. You're going to need a periodic table to use in our calculations, and you will need your textbook. And the first thing that we will be looking at is on page 354. All right, let's go through. Start at the top of the notes on page 1. So a lot of vocab actually on this first page. So this chapter is about solutions. All right, some vocab here. The solute, that's how you pronounce it, solute, is the substance that's being dissolved. Okay, so if you were dissolving salt in water, the solute would be the salt. The solvent is the substance that dissolves the solute. So water is usually our solvent. Okay, it's usually a liquid. Why do solutes dissolve? So let's look at figure 11.3 on page 355. So let's look at this figure here. So why do solutes dissolve? Well, for example, with sodium chloride, sodium has a plus charge, chlorine has a minus charge. Chlorine is this big green circle represented, and the sodium is this little red circle. Water, of course, we talked about in chapter 9, is polar covalent. All right, so the oxygen which is blue here, has a partial negative charge, and the hydrogens, which are green, have a partial positive charge. So the sodiums, the positive sodiums, are attracted to the negative oxygens, and the positive hydrogens are attracted to the negative chlorine. So that water, as it works its way up in here in between the sodium chloride crystals, breaks apart the sodium and the chlorine and causes that solid sodium chloride to go into solution. Okay, so you can read through this explanation. I talk about that, but I have linked a video in the description box called the Dissociation of Salt. And watch that video. It's very short, and it kind of puts a graphic visual to this process. All right, when something's called insoluble? That's when the attraction between ions is so great that water molecules or any solvent can't force their way in between. So some things just simply won't dissolve. Polar covalent substances dissolve the same way as ionic compounds, all right? So that's a picture of that. If you'll turn the page in your book to page 356, all right, you can see pH3, which is a polar covalent compound being dissolved in water. Instead of breaking up into its constituent ions, however, each pH3 molecule breaks up, but it still goes into solution. It's just not positive and negative ions. It's the entire molecule that goes into solution, but a very similar process. Now, you can also have liquid solutes. You can dissolve liquids into other liquids. All right, and since liquid solute molecules are not very close together, where a solid has molecules that are packed in tightly, it's not very hard for solute molecules to get between them. However, there must still be an electrical attraction in order for liquids to dissolve other liquids. So an example is alcohol is liquid ethanol or methanol dissolved in water. All right, so you have a case of a liquid dissolving in another liquid. You can also have gaseous solutes, and we talk about gaseous solutes. What I want you to think about is a carbonated drink. Okay, why is it fizzy when you drink it? Okay, why when you open the cap or pop the top do you hear a psh? Okay, it's because you have CO2 gas dissolved in water. All right, so the solvent molecules must attract the gas solute molecules to them, and since gas molecules are far apart, the solvent acts like a magnet. So what I want you to do sometime as you study this chapter is look over the table on page 358. You see this table. Look over that and the solute phase, solid, liquid, gas, and just read through that table, and it explains how each one of them dissolves. Okay, so you'll need to know that. All right, let's take a look at solubility. All right, so solubility is the maximum amount of solute that can dissolve in a given amount of solvent. Okay, so solubility is reported in grams of solute that will dissolve in 100 grams of solvent. Or an example of that would be 10 grams per 100. So for sodium chloride, I don't know if you can read it, so I'll write it on the board. For sodium chloride, its solubility is reported in water as 37 grams per 100 grams. So 37 grams of sodium chloride will dissolve in 100 grams of water. If you do 38 grams in 100 grams of water, 1 gram of that is insoluble. All right, it won't dissolve, okay, because you've reached the maximum solubility of NaCl in 100 grams of water. Okay, solubility is different for each substance, and a saturated solution is a solution in which the maximum amount of solute has been dissolved, and I will show a demo of that in class with a test tube, and I'll also have a demo with gaseous solutes where I do a pH demo there. All right, turn your notes over. So we have a table here called the effect of temperature and pressure on solubility. So for example, if you have a solid solute, if you increase the temperature, it increases the solubility. You can dissolve more solid if you'll increase the temperature of the solvent, if you'll heat up the water, so to speak, okay? Because increasing that temp gives the solvent more energy. Increasing pressure has no real effect on solids. Okay? For liquids, increasing temperature and pressure has no effect on solubility. On gases, if you increase the temperature, it decreases the solubility. Let's think about this a second. If you have a carbonated drink, all right, you take it out of the fridge, okay, will it go flat faster outside of the fridge or in the fridge? It goes flat faster outside of the fridge if the temperature is higher, because the gas molecules are moving faster with a higher temperature and have more energy to escape the liquid. On pressure, however, if you increase the pressure of a gas, then that would increase the solubility. The pressure is a way of holding those gas molecules down into the liquid. That's why the contents of a carbonated drink are under pressure. When you take the cap off, you hear that psh. All right, the contents are under pressure to help keep the gas dissolved. So reading through the reason, increasing temp gives gas molecules energy to escape. Increasing pressure forces gas molecules closer together. I will link a video in the description box that you need to watch called Henry's Law that helps to understand the solubility in terms of temperature and pressure. Let's look at on your own 11.2, 11.1, 11.2, and 11.3 real quick. So in your book, we are on the bottom of page 362. All right, so in 11.1, says that a student is asked to dissolve 50 grams of potassium chromate in 250 milliliters of water. He's having a hard time getting all the solid to dissolve, but is not allowed to add any more water. What should he do to try to make all 50 grams dissolve? Well, solutes increase the solubility if you heat up the solvent. So you would add heat. That's the answer to 11.1, add heat. All right, 11.2. So it says a chemistry lab is storing several bottles of a solution made by dissolving methane gas in octane, a nonpolar liquid. The laboratory chemist notices that every once in a while the lids from the bottles pop off. She reasons that the lids are popping off because the gas that is dissolved in the liquid is escaping from solution. What can she do to stop the lids from popping off? Well, she could increase the pressure, but that's not that easy to do. The easy thing to do to make a gas more soluble is to decrease the temperature. So put it in the fridge. Right? Again, think of that carbonated drink. Why do you store it in the fridge? To keep those gas molecules moving more slowly so they won't escape. They won't hit the surface and escape. All right, 11.3 says a student is doing an experiment that involves dissolving a gas in water. He notices that even though the temperature in the lab is exactly the same every day, there are some days in which more gas can dissolve than other days. What most likely is changing from day to day in order to produce this effect? I don't know if you ever watch the weather, but they always give a metric that most people don't pay attention to, and that is barometric pressure. So the air has a different pressure every day. So the air pressure is changing. So on a day where you have higher pressure, more gas will dissolve. On a day where you have lower pressure, less gas will dissolve. All right. So that takes care of 11.1 to 11.3. Let me just draw a little diagram. Let's say we have a beaker. Let me describe this air pressure situation a little better. And let's say we've got some water in that beaker and we have some dissolved gas. And we'll just represent that dissolved gas with dots. Those molecules are moving around. Some of them hit the surface and escape. They will stay dissolved if you have a higher air pressure. Think of the air pressure as kind of like a cap on the surface of this water that helps keep those gas molecules in solution. All right, so if you need to, pause the video and we'll move on to the next portion of the notes. Okay, a little more vocab. We're at the middle of page 2, so energy changes and solutions. An exothermic process releases heat when dissolved. All right, I'm going to demonstrate that in class by doing an exothermic reaction. You'll see how hot the beaker gets. An endothermic process absorbs heat from the atmosphere to dissolve. Okay, so you might think of if you ever hurt yourself, sprained an ankle, maybe someone got you a cold pack. All right, so that cold pack was room temperature, and then when you broke it, it suddenly got cold. That's an endothermic process, gets colder, and I will do a demonstration of that in class. Most solids dissolve endothermically, so you might not be able to tell it because it's slight, but when you dissolve solids in liquid, usually the liquid gets a little cooler, sometimes a lot cooler. All right, let's look at on your own 11.4. And you can see in the book how it talks about on page 364 the hot pack and the cold pack. 11.4. Okay, and says the following reaction is carried out in the laboratory. I'm going to write that out on the whiteboard in a minute. It says if 125 milliliters of 0.5 molar H2O2, we're on page 367 by the way, is reacted with an excess of other reactants, how many grams of oxygen will be produced? All right, so let's write out this reaction. You've got a spot on your notes. It's 11.4. So we have 5 H2O2. I'm not going to write the phases right now. 2 KMnO4 plus 3 H2SO4. So this is already balanced for us. Yields 5O2 plus 2 MnSO4 plus K2SO4. What a long reaction. Plus 8 H2O. All right, it says we have 125 milliliters of 0.5 molar H2O2. Let's write down what we know underneath each compound. 0.5 molar. All right. How many grams of oxygen will be produced? This is exactly like one of the types of problems in chapter 10. All right, so you're going to get another crack at it. So first of all, we need to get moles of H2O2. If molarity is equal to moles per liter, then if we rearrange this equation, moles is just molarity times liters. All right, so moles of H2O2 is going to be 0.5 molar. We have to change that 125 to liters, so 0.125 liters. All right, if you put that in your calculator, you get 0.0625 moles. All right, now we're going to do a little stoichiometry. So we got 0.0625 moles of H2O2. Put that over 1. We need to go to moles of oxygen. So we have 5 moles of oxygen. And it's a 5 to 5 ratio. All right, so we're not going to have to do a lot of calculator work there. 5 moles of H2O2. And then if you look on your periodic table, each oxygen weighs 16 grams per mole. So that's going to be 32 grams of O2, since there's 2 of them, over 1 mole O2. So in your calculator, 0.0625 times 5 over 5, so just times 1 times 32. And that is 2 grams of O2. So just like chapter 10. All right, let's see if I can squeeze on your own 11.5 underneath this. All right, 11.5 is a lot of text there, so I'm going to let you read through the informational part. We'll write this reaction down in a minute. But it says if the mixture of these two metals contains 1.2 kilograms of aluminum, how many liters of 6.5 molar NaOH solution would be needed to make sure that all the aluminum was taken out of the mixture? All right, again, read through that yourself. I won't read it to you. Let's write down the reaction and write down what we know from the problem. So we have 2 aluminum plus 2 NaOH plus 6 H2O. And that yields 2 NaAl OH4. Excuse me. Plus 3 H2. All right, so what do we know? We know we have 1.2 kilograms. Be careful with those kilograms of aluminum. How many liters of 6.5 molar NaOH? So how many liters? Well, if molarity is equal to moles per liter, then we know we can solve for, it says how many liters. If you're solving for the one on the bottom of the fraction, just switch with the one out front. So liters is equal to moles over molarity. I know molarity, so all I need to do is get moles. Okay, so we have 1.2 kilograms. That's 1,200 grams of aluminum over 1. Let's go to moles of aluminum. If you look at your periodic table, aluminum weighs 27 grams. Now we need to go to moles of NaOH. So we have 2 moles of NaOH over 2 moles of aluminum. So we have a 2 to 2 ratio. All right, putting that in your calculator, that's 44.44 moles of NaOH. Now you have what you need to get the liters. So liters is equal to the moles, 44.44, over the molarity, 6.5. So again, just a rearrangement of the molarity equation. You put that in your calculator, you're going to get 6.84 4 liters. All right. So pause the video if you need to, and we will work. I'm just going to teach you one more concept in this video. Okay, turn your notes over to page 3. I'm going to talk to you about another concentration unit. So we talked about molarity in chapter 10 in the beginning of chapter 11. This concentration unit is called molality, and we use a small m. And that's the number of moles of solute for kilogram of solvent. All right, why would we need another concentration unit? Well, sometimes it's actually really hard to measure the volume of something. With this, we can just weigh it. Okay, so our formula is little m, molality, is equal to moles per kilogram. All right, going to need to memorize that, moles per kilogram. All right, so let's just work a few problems where we calculate molality. Look at on your own 11.6. This is on page 369. All right, so we're going to calculate the molality of the following solutions. 2.3 moles of NaOH dissolved in 1.2 kilograms of water. Part B, 250 grams of KNO3 dissolved in 2.43 kilograms of water. And then finally, part C, 34.5 grams of sodium bromide dissolved in 578 grams of water. All right, so this is pretty much just plug and chug. We're going to use molality with the next lecture. So 11.6a, our molality is going to be 2.3 moles over 1.2 kilograms. So we don't even have to do any conversions there. So that's 1.92, and you just use little m, a molality of 1.92. All right, B. This time we were given grams of the solute, so we have to get that to moles. So 250 grams of KNO3. We're going to go to moles. All right, take a look at your periodic table to get KNO3 for potassium, 39.1. For nitrogen, nitrogen is 14. And then oxygen, each oxygen is 16. So if you add that up, you'll get 101.1. Right, so 250 divided by 101.1 is 2.47 moles. Don't circle that. That's not the answer. We have to get molality. Moles per kilogram. So 2.47 moles in the numerator. And in the denominator, the problem said it was 2.43 kilograms. So this is going to be right at 1. It's a molality of 1.02. Sometimes they say 1.02 molal, but that's kind of a tongue twister. So 1.02 molality. All right, and finally, the last problem of the day, part C, says we have 34.5 grams of sodium bromide. We want to go to moles. Okay, add up sodium bromide and you're going to get 102.9, so from the periodic table. So that's 0.335 moles. And then we get the molality with moles per kilogram, so 0.335 moles. Now it says we have 578 grams. Well, 578 grams is equal to, divide by 1,000, move that decimal point 3 places to the left. That's 0.578 kilograms. Remember, we have to change it to kilograms. So that is a molality of 0.58. All right, just give me a second and I will tell you what the homework is related to this lecture. So pause if you need to. All right, the homework is review questions on page 381. You can do 1 through 9. Okay, most of those come from that first page of notes and a little bit of the second page. And practice problems on page 382. You can do 1 through 7. All right, thanks for watching, and I will talk to you next video.